So we're going to talk about the derivative at a point, and to start this off, before we even get there, what I want to talk about is a tangent line. So we had an activity where you explored tangent lines at points on graphs of functions by zooming in and thinking about that graph being locally linear. Okay, so that's a great way to think about tangent lines. We can also think about tangent lines as limits of secant lines. So remember, secant lines are on graphs of functions are lines that go through two particular points on graphs of functions, and they're over an interval. So what I want to think about is the tangent line as a limit of secant lines now. So when we were discussing average rates of change, we had this function, x squared plus 3x plus 1, and we found the average rate of change from x equals -4 to x equals 0, and then we viewed it as a slope of the secant line between these 2 points. Okay, so what I would like to do is instead go ahead and think about, instead of an average rate of change over an interval, what's going on? Actually think about what is the rate of change right at this point right here, right at this point, -4, 5. How is the function changing at that point? Is it increasing? Is it decreasing? What is it doing exactly? You should be able to look at this graph and say, oh, right at -4, that function is decreasing. It is going down from left to right. So somehow we should get this notion that it's going down, and how quickly is it decreasing? So what we want to know is, what is the slope of this secant line as this interval gets smaller and smaller and smaller? So I think of this tangent line as, what is this secant line as my interval gets smaller and smaller and smaller? And you can see that when my h is 0, that line goes away. But everywhere else, that's a secant line, and I want to know, what is that line as these 2 points get closer together? So I can also think about the tangent line as the limit of a secant line. So now we actually want to define a derivative. Okay, so we're going to start with the derivative at a point. So the derivative of f at x equals a, so we're always talking about a derivative at an x value. Okay, I think about this as a rate of change at a. How is the function changing at x equals a? Okay, so I want it exactly at a, not over an interval. How is it changing exactly at a? So again, I'm thinking about that tangent line being a limit of secant lines. We think about average rate of change as the slope of the secant line there. So here's my average rate of change formula. And what I want to do is make that interval go over, get smaller and smaller. So I want to change that interval length h into smaller and smaller values. So what I'm going to do is I'm going to take the limit as h goes to 0. And this is my computational definition of the derivative. And I write it as f prime of a. This f prime of a is the notation for the derivative of f at a. Okay, this is my definition for the derivative. And if this limit does exist, if that limit exists, we say f is differentiable at a. Okay, if the limit exists, we say it's differentiable. So let's go ahead and compute this. Okay, so let's find f prime at -4, where f of x is this function we talked about, x squared plus 3x plus 1. Okay, So let's go ahead and set it up with that computational definition. F prime at -4, this is the limit as h goes to 0 of f of -4 plus h minus f of -4 divided by h. And that's a computation we're going to have to do. Now you've seen why I made you do this computation without the limit several times before starting now. Okay, so I'm going to go ahead and compute this. Go ahead and see if you can at least algebraically manipulate this expression before I do it. All right, so just here's our function. F prime of -4 is this limit. And so let's go ahead and do it. We get the limit as h goes to 0 of -4 plus h squared plus 3 times -4 plus h plus 1. So that's the f of -4 plus h part. And then this minus 5, that is f of -4, all divided by h. Okay, so let's do some simplifying. We went ahead and expanded out that square, and it's h squared minus 8h plus 16. All of that is that -4 plus h squared, plus 3 times -4h. That's the -12 plus 3h. And then I combine the 1 and the -5 to get -4. And then keep combining. It simplifies quite a bit. We get limit as h goes to 0 of h squared minus 5h divided by h. Yes, I do have to keep writing this limit as h goes to 0 each time. They're not equal without that limit. Okay, so we can factor out an h and get limit as h goes to 0 of h minus 5. And now we're really ready to take this limit. Before, every time, like here, we would have gotten 0 divided by 0, which means that we need to do something else. So now we're ready to take that limit and we get -5. Okay, so what does that mean? It means that f prime of -4 equals -5. In fact, if we know that f of -4 equals -5, that's the rate of change of f at -4. And what that means is that if I consider the slope of the tangent line at x equals -4, let's try to do that. Slope of the tangent line. I'm taking the tangent line to this point of that function. There's our tangent line. And look here, if we look at this definition of this line, it has a slope of -5. That is the tangent line at x equals -5, at x equals -4, and it has a slope of -5. That's our derivative at x equals -4.